My name's Jared. If you're new here, I'm a Rubyist. I run a software company called Supergood Software, where we build e-commerce systems using Ruby on Rails and an open source platform called Solidus. We have completed so far this month days 1 through 22 of the Advent of Code. I don't know if you want to call it competition. We're not really competing here, but certainly a fun time. Remaining are days 23, 24, and then 25's an easier one, I'm told. It usually is. So I'm about to head into, not being right back, but in fact, day 23. Kind of putting this off because we're already past Christmas here. It's the 27th. I'm obviously behind, but I just didn't like I just didn't want to do the work on this one, but I gotta do it. What is it? Fear not the task ahead. There's no escaping it. A group of amphipods notice your fancy submarine and flag you down. With such an impressive shell, one amphipod says, surely you can help us with a question that has stumped our best scientists. They go on to explain the group of timid, stubborn amphipods live in a nearby burrow. 4 types of amphipods live there: amber, bronze, copper, and desert. They live in a burrow that consists of a hallway and 4 side rooms. Side rooms are initially full of amphipods, and the hallway is initially empty. They give you a diagram of the situation, your puzzle input, including locations of each amphipod. A, B, C, D, or D, each of which is occupying an otherwise open space. Walls, hash, and open space dot. The amphipods would like a method to organize every amphipod into side rooms so that each side room contains 1 type of amphipod, and the types are sorted A to D, going left to right like this. Makes sense? The amphipods can move up, down, left, or right so long as they are moving into an unoccupied open space. Each type of amphipod requires a different amount of energy to move 1 step. Amber amphipods require 1, bronze 10, copper 100, and desert 1000. The amphipods would like you to find a way to organize the amphipods that requires the least total energy. However, because they are timid and stubborn, the amphipods have some extra rules. Amphipods will never stop in a space immediately outside any room. They can move into that space as long as they immediately continue moving. Specifically, this refers to the 4 open spaces in the hallway that are directly above the amphipod starting position. Excuse me. Amphipods will never move from the hallway into a room unless that room is their destination room and that room contains no amphipods, which do not also have that room as their own destination. Makes sense? So if there was an A here and a D here, it would never move into here. Once an amphipod stops moving in the hallway, it will stay in that spot until it can move into a room. That is, once any amphipod starts moving, any other amphipods currently in the hallway are locked in place and will not move again until they can fully move into a room. In the above example, the amphipods can be organized using a minimum of 12,521 energy. One way to do this is shown below. What is the least energy required to organize the amphipods? Interesting. You know, I think so we have our own input. It is different from the example. Well, okay. All right. So let's get down to hacking this thing here. Where'd you go? There we go. All right, so we're on day 23. So let's click on day 23 spec. And day 23 part 1. Sorry, my fuzzy match will look different on my stream setup than it does in my regular one. I'm gonna have to line everything up at some point. With me, I'm a little dehydrated today. Now we could pop our input in here and like parse the input. I feel like that's not super valuable though. But I guess we kind of have to if we want to be able to handle different inputs. Whatever, sure, let's do it. So I think we're just going to do a search through the state tree because they put enough restrictions on it that I feel like that's doable, and specifically that there's some optimizations I know we can do. So we're going to need to be able to just at least represent the state of the current state of this thing. So I feel like it'll be worth having a state struct. The state struct is going to need to have room A, room B, room B, room C, room D. And let's just try and understand this. Once an AirPods stops moving in a hallway, it will stay in that spot. So AirPods will never move from a hallway into a room. Never stop in a space immediately outside any room. They can move into that space as long as they immediately continue moving. Specifically, this refers to the 4 open spots. They can't stop here. Not here or here. They can stop in those ones, and they can stop in these ones. Just trying to decide whether I like model this as an actual like coordinates. Kind of don't want to. I'm just not sure how I model the hallway now. I guess the hallway is just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 positions. And with 4 indices that are you're not allowed to stop in. Oh, there's just so many little bits to this. It's going to be so annoying. Okay, so we've got a state. So this, I don't want to be able to create a new one. But the hallway can't necessarily be an array. And how many decide here? 1, 2, 3, 4, 5, 6. There's 11. And then this is a better or worse way of modeling this than anything else. I feel like any option is going to be reasonably complex in terms of what I have to do here. How do I take this input? So input grep, that's initial equals state parse input. Strip it. Let's just play around with it. We can focus this spec. It's the one we'll be working on, and we can set the effective value for this example is 12,531. And our spec, and I have an input. We can strip and join, or no, we haven't split it on anything. If we just G sub something, like all the I want tubular. That's what I want, a non-word character. Oh, I didn't. Huh. I don't need a plus there. I just need non-word characters. There we go. Okay. That just rips the letters out, which is fine. We can just put them in the way we want. So room A is going to be letters 0. Or no, it's the second one. We want the end of it to be the top, I think. I don't know. Letters 0, 1, 2, 3, 4. And this will be 5 and 1. All right. Looks like it could be right, but I think what I want to do is I want to just go ahead and implement a way to print these things. So it's going to be let's change. I mean, I guess maybe I can 3, 4. Let's just copy this over. This is going to be hallway dot map X or dot. Dot join. Okay. Okay, that worked. And now we just need the other ones. So this is going to be room A 1. B1, C1, D1. Yeah. The domain was available. All right, so that prints out fine. Spaces around it just to make it. It's not code's not pretty, but there we go. BA, CD, BC, BA, which I believe was the right input. BA, CD, BC, BA, yeah. Okay, so now we know we have a map of where everything goes. So I think we do. I think we can do some amount of just sort of like traversing the possible states here and picking the cheapest options first. A lot of people noted that you can kind of do this one relatively easily, I think, by pen and pencil. I'm not going to bother doing that, but apparently it's an option. So I think you want to be able to have like a next states. Do we want to have a cost associated with this as well? Need that? Let's just try and start writing this code. So let's put this here. Next states. So we only have so many moves we can possibly make, right? We have, we can move. Oh, let's just make it actually possible moves. Not just, and I'm talking just in general here, not just for this particular state. So you can move amphipods into the hallway. Move, let's call them available amphipods to the hallway. So that's amphipods that are not blocked and that are not already correctly situated, like this one. So this one would be blocked. This one's already correctly situated. So even if B wasn't there, yes, but not any position in the hallway. Good observation. We only have 1, 2, 3, 4, 5, 6, 7 possible positions. Some of them might be blocked. We can move amphipods in from the hallway. Now, it's going all right. We're not too far into this one. Just working through the problem, trying to understand the possible moves we can make here. But I guess that's it, right? The restrictions are like, once it stops moving in the hallway, it will stay in that spot until it can move into a room, right? So currently we've got no options in our initial state. We have no options to move them in from the hallway, and 4 options for moving into the hallway. And each of those 4 can move into 7 different positions within the hallway. And maybe we'll, so we can, this just needs to return an array of the possible next states. And our next states here are going to be our, let's call this moves into hallway. We'll just flat these out. I guess we can just call flat on this thing. Moves into hallway, moves out of hallway. Oh yeah, could call it moves into room too. That's and since we can get into the next state without ever doing a moves into room, we might as well start with moves into hallway. So what's our collection we want to iterate over here? So we have 4 rooms and we need to check which ones have, we could just check all of the positions in the rooms, validate each one. But now let's go room by room. So we'll go, how am I gonna do this? This is a little tricky. I want to first figure out it's just a little tricky to parameterize since they're all dependent on the state. I need another coffee today. If I mean, I want to just loop over the rooms, but I need to know. So awkward. I was dreading this one. Because there's gonna be at most 4 move, or not at most 4, most 4 tiles that can move here. So we'll say if public send room empty, So we'll be doing a flat map here, so might as well do that. So if there's no one in this room, we don't have to do anything. There are no possible ways to move any of them out of an empty room. And then it's a matter of, okay, if how am I going to do this? I kind of want just like a mapping of states. So I want like room mapping. Just so I have a way to look up based on the room name what letter is supposed to be in it. So if so, all right, let's say room content equals this. So we got room contents, we got an early return, and then we want to say if room. Yeah, it's gonna be a pain, but I assume it's day 2's or the part 2 is gonna be somewhat more difficult in some way. Room contents all so if the room, if the contents are the room are all if everything belongs, then we don't need to do anything. And then finally, it's just a matter of whether we pick B and whether we can pick A. If so, I guess room. I'm gonna map these so last. So we know this isn't empty. We're not. Will contain nils. We're using nils for the placeholders in this one. So this is the handle first. Oh, we're gonna hand it the last. If so this is if room.last no, we don't care what it's equal to. We know we need to move it out at this point, regardless of what it is. Okay, so now we're here. We're like compute possible hallway moves. It's non-trivial. We'll have to get to that in a sec. Otherwise, it is nil. Then if room not first does not equal room mapping room. Oh, these are supposed to be returning, so these are supposed to be next. So I guess this is next, no moves. This is for room first. This is for room last. Oh, this is so annoying. Just so much stuff we're gonna have to figure out to get this to work. And so many moves we're gonna have to do, like so much we're gonna have to do to make any progress. Now you got me thinking about pen and papering this one. Okay, let's keep going. So let's just think through this. We're gonna move up one, move one, left, right, valid additions. God, this is such a string puzzle. Yeah, I mean, I'm essentially treating them as stacks. Maybe not as nicely in the code as they could be, but yeah. I'm vaguely tempted to yeah, I'm almost tempted to model this as a graph though. It just seems like so much work. But at least then I can do sort of graph movement. I don't think that'll make this easier though. That's true. That's true. So let's start here. So cost equals, in this case, our do we just iterate over the valid possible ending room positions? I'll need to bake in some code to figure out if they're blocked. That's not so hard. Rooms is just about pushing and popping until all have the right letter. Yeah. All right, so let's try this at the other case. Let's just swap these. This is the one we're going to look at first. So let's say, so the possible end indexes are going to be 0, 1, not 2, yes 3, not 4, not 4, yes 5, 6, yes 7, not 8, yes 9 and 10. That is this one, these two, this one, that one. Come on, let's put that one, and those two. Okay, what am I doing? So for each ball, we're doing next unless the position is possible. We'll figure that out after. And then we're going to have to create a new state. Create a new state, or just use these immutable structy boys. This is so annoying. So I know this is the last move in one of the rooms. This is where I'm really questioning whether this is how I want to model it or whether I want to just go the grid approach, because this seems really annoying. This is already feeling like a really just painful approach to take. I kind of just want to keep track of a bunch of XY positions of these things and just move them around. Because the cost of moving them is just their like Manhattan distance to where they end up. Yeah, that seems like a better way to do this. Oof, already 44 minutes in. Not made a lot of progress here. Okay. Because I don't need a lot of this junk if this is the approach we take. I don't even think I want a keyword in it at this point. Oh, but I have a cost. Yeah. Oh, I can't do that. I hope they would let me do that. Break them all into new lines. And so we should know, let's just sort these. We should know the coordinates of them all. So 0 is going to, let's just actually put placeholders in all of these. Okay, so we'll consider this to be 0, 0, which means this can be 2, 1. Numbers 1 can be 4, 1. I mean, those are just, this is just a hash, but the keys are arrays with 2 numbers in them. The keys in a hash can be anything hashable. No special syntax here. Just friendly neighborhood Ruby. Very useful pattern though in a lot of these problems because it allows you to do like fast lookups of things. I'm just gonna nuke all this code we wrote. Yes. Yeah, it is. It is kind of weird, I guess. I don't really know how it makes that work, but I've never really like, I don't normally mutate the keys though. Like, wait. Hmm. Well, this isn't working very well. What? So I guess the answer is that it doesn't work very well if you mutate the keys in your hashes. Um, that's funny. Okay. Lesson of the day: don't mutate the keys in your hashes. Um, now where was I? Sorry. Okay, so our print is now totally not working. So this is going to be 0 to 10 map positions. We're going to look them up by their x value and 0. Or period. Oops. Where's back it now? Cool. Looks like it worked. This is ugly as heck. Four, 6, 8, and all of these ones should be 2s. It should. Oh, I guess I should have just. I just do. There we go. Work. Yeah. Basically, we've got some extra lines, extra walls, but there we go. Now it's exactly the same. Okay. So I want to take a little break from that now, because we can go positions.keys each do each flat map, I guess. That's not a thing. So probably want to just break this into the XY already, I think. If we just put I'm just gonna call initial.next states. I want to hit this code. Cool. I have an X, I have an Y. That works exactly as I expected. Now we're going to say if Y is greater than or equal to 1, this means we're in a room. Else we're not in a room. Sorry. I'm just not very good at drinking water. Okay. So we can say if Y equals 2, yeah, this is way easier to do in terms of coordinates. It's like I know what range I need to check the positions in the hallway. I know a lot of stuff that's easier to think about this way. So if Y equals 2, then we need to check. We need to next if positions X1 or we can say unless or maybe we just make this a single guard clause. Next, if Y equals 2 and so that is fail if we're stuck in our room. Okay. So that means, or sorry, I guess fail is a bad word here. Do nothing if we're stuck in a room. Okay, so we know we're not stuck in a room at this point. We don't care whether Y is 1 or 2. We just want to get out. Less than or equal to 1. Greater than or equal to 1. No, I'm the tired one, not you. It's either 2 or 1. So we do not think we're stuck in our room. Else we can evaluate the possible hallway positions, which, see, dog's here. Sorry, I can't easily turn the camera down. So we want to loop over the possible end rooms, which are 0, 1, 3, 5, 7, 9, and 10. each we'll map these hallway X. Oh, we'll compact those to remove no values because there could be no values. So we'll next if false. Check for blocking. If there's no blocking, then we can compute the cost. And let's just make sure I'm remembered how we're doing that. Let's try a new one of these. So if we've got our zero, zero, we've got somebody is in, say 2, 2. Should be absolute value of this of the difference plus absolute value of this difference, right? 1, 2, 3, 4. Yeah. So cost is going to be x minus hallway x abs plus y minus, I guess it's just y minus 0 because hallway y is 0. And then we're going to multiply that times the cost of this fellow, this amphipod. Costs. I've just been informed that it is snowing again. Got ourselves a somewhat white Christmas. Show you. That's what it's looking like outside of our place. Roxy was just looking out the door. So when costs, we knew at some point we would have to model that in here somewhere. So we'll just map our costs. I believe that's what it said, right? A1, B 10, C 100, D 1000. Okay. So then we'll create a new state, self.class new, that's in the additional cost plus cost in there, and we will the current, it's going to be positions merge, and then we're going to provide a couple extra positions. So XY actually I can just do positions. New positions equals positions.dupe, and then we'll new positions delete one removed. And then we're going to set this is going to be hallway x and 0. That makes sense. Okay. Need to fix that. Let's see if this produced something. Let's try and make this work. Okay, so it has created a number of next states. Does this look like all the... Oh, we've got an issue here. We are moving out the wrong ones. Something is wacky. Two. We can. It looks like the wrong ones are moving out. So we've got a bit of an issue there. Oh, this is backwards. Interesting. I feel like this is still not doing the right thing, but okay. It's produced fewer. Looks right. That now actually looks right. We nice to print their costs alongside them. C is going to cost 110. I don't have any A's to move. It's coherent. Okay, so I mean we can now try to take a step back No, do we want to take a step back? Maybe it's time to take a step back. Think about the like tree traversal here. So what are we doing? We're trying to find the cheapest cost. So So return the cost of this, getting to here. And we're done. Otherwise, we return next dates, map, cheapest cost, compact, min. We can implement done pretty easily, I think, because we know that it's going to be the list of. So we want 4-1. 2. We're gonna do this. What's 2? Oh man. I keep forgetting that. I'm one of those Vim quirks. Sorry if there's background noise right now. I think my audio might like cancel. It'll probably cancel it out pretty good. Unless I'm talking. I think that's how we check if we're done. And then now I think want to do that. Got 0. Intriguing. Doesn't seem right. Done. True. Sure. Despite that clearly not being correct. What? Oh my god. Okay. This not. There's an array containing a hash. So that's funny. Cool. We can print the state now. B has no valid moves. And it could only possibly have 2 valid moves. Only for B, we only need to look at these 2. That one and that one. So I think we can. We're just gonna. In that case, positions Y, 1 A. Okay. So let's handle B first. So the only time there's only 2 possible moves, only one of them will be valid. So we can check the first one. We can check to see if positions, let's just make sure we get that right. It is 0, 1, 2, 3, 4. So it is 4, 0 and 4, 1. 4, 0 is no. We'll try to move in there. Again, we're gonna have to do some checks if that's passable, because there could be something sitting right here. We've not handled that yet. So 4-0 is nil. Check if it's passable. Else we are moving into 4-1. Feel like we can generalize this code. Let's just try and move forward for a sec here. We're going to do a similar thing. As we've done there. Well, we shouldn't have any we shouldn't be iterating over any positions where the keys are nil. We're removing keys where nothing's there anymore. And then, thank you. Coffee. Oh, you're right. My second one totally is reachable. We shouldn't have, so we're iterating over the keys in our positions hash, and the keys should only ever be set to A, B, C, or D. We're deleting values when we move amphipods out of those cells, so there won't be any like nil values or anything that are actually in the keys hash. Thanks for keeping me honest, though. Okay, so where are we here? Let's ignore the passable checks, and then we'll say if so. Right, what was it doing? I'm doing this. We're assuming we can get in here. And we're just going to return this, except that doing different things here. So we're at the additional cost. It's 4. Oh, this isn't 0. This is 2. Yes. So that and hallway X is just 4. Ooh. Just 4. So if that's passable, and this is the same thing, except that this should be a 1, this should be a 1. Why did I say 1B? Oh, right. But in reality, these are all going to be the same, just with different. So we can even say, we can generalize this right ahead. We'll say destinations equals 2, 1, sorry, 2, 2, 2, 1. 6, 8, 4, 6, 8. And then you can index this by friend here, and kind of just closure levels of nested angle or square brackets, and then this logic's all the same. Let's cut all that out. Cut all this out. Cut off the conditions. So destination equals destinations. Find. We want the first one that's not nil. Return. We just next. We're inside of a. So we'll next nothing unless destination. Now, just to keep it spicy, both are nil. You want the bottom slot. Yeah, that's why I'm checking them in that order, because if the bottom one is nil, then the top one is going to be nil, because there's no reason I would end up. I don't think we can end up in a state where there's one on the top, but not one on the bottom. I think the rules prevent that from happening. I'm going to call this dest because I don't like typing. Step first, last, dest. So we got a lot of stuff in here, but the code might run. I find with the cheapest cost for nil class. 8. Oh, what did I do? Next state shouldn't contain any nil values. Oh. Cool. So now we are, like, I'm aware that we're going to need to do some amount of optimization here, or some dynamic programming or something, once we get this within the realm of working. Well, that's fun. Not useful. Doing something though. So let's take a look. What should we work on next? We know we have to do blocks for checks for blocking. In this one, Do nothing if we're stuck in our own room. We also want to do next if we're correctly situated. If correctly. We probably reuse that for this whole thing. Maybe? False unless position dot y if position last equals 0. If you're in the hallway, couldn't be in the correct spot if we're in the hallway. What is this about? Just apologies, I have a great many text messages. Ooh, new gaming headset I got. It's just arrived. Exciting. I'll be using that tonight. All right, hour and a half in. Okay. I ended up streaming 4.5 hours straight to do day 18 or whatever that was. Turn false position 0. I feel like this mapping is good. So if there's 3 cases, so position last is 0, then return false. Else if position last is equal to 1, then we want to return if we want to return weird, correct, and y equals 2 is correct. Else only carefully correct. So we're gonna copy this out of here. Call this final. I'm gonna reuse it. It seems useful, you know? So in this case, this is the simplest one. Final position equals positions position. And then this one is final position is this and correct. Okay, so that's gonna limit our moves further. Reasonable. Oh, let's print them out. I like the okay, so we can see A and C are chilling. There's the dog. Here, I'll be right back. Apologies. My parents were just dropping a Christmas present, and it's something that warranted charging, so it'll be ready for tonight. So I had to get out of the box or anything. So that's fun. That's running forever. So now we have to determine if things are passable or impassable. That should not be difficult. So let's say next if passable. So we'll say we'll give it 2 start and a destination. A good way to do that. Do the same here. Here the destination is going to be I don't think start will ever be equal to finish. So start's less than finish. Then we need to evaluate all the values from start +1 up to finish. And we're going to be doing it down to start -1 down. Positions x 0. Yeah. And this is -1 down to finish. That's vaguely right. Okay. It's up to the same. Yeah. Random standard library things where they're just like, we changed our mind. Okay, that's not great. Okay, well, that's starters. That's wrong. Less passable. This should also be less passable. Okay. We're certainly getting more values into positions. I wonder if we're actually getting are we actually getting deep enough in here to get any done values? Probably want to search through the cheapest options first. Isn't getting us anywhere. That's gonna be the opposite of what I want, or what I want. Yeah, that's what I want. Was able to get the first 3 in. It's generally producing smaller values here. Previously in our searches, we were seeing a lot of big values. So one thing I want to do is, I know I want to just give up if we reach a state and we've already reached that state before through cheaper means. I'm wondering if cost shouldn't be part of the state. This is so far never getting to a finished state, which is worrying me. Also, also return if cost is greater than 12,521. And what's going on now? I remove the print. I'm sure we can pick a better value than that for the actual run, but just curious as to why we're getting so few states. Something's weird. I feel like maybe our moving things back in code isn't right. This is our initial state. I use map, I will return nil, so it'll be easier to read. So like we can see, okay, so let's get down into an additional state. So we're in this state, we're in this state now. So this is like an obviously invalid state. So B just disappearing, not a valid next move. So that's suspect already. So the other ones look pretty valid though. B can go there, B can go there, go there, C can go there, C can go there, C can go there. And this, and D can move out. We don't have any options of C moving out, which is interesting. So that's wrong. Okay, so that helps. So in this case, we're getting something wrong. So let's step through this and just see if we can figure out what it is just by, well, I never turned my streamlining on today. Huh. Need like just a button I hit to do it. Yeah. Nice, even lighting on me. Which is actually just the bias lighting on my desk, and on the lighting that's the lamps that are pointed at the walls, I'll just going white, reflecting it on me. So the position is going to be, it was a B I think we were looking at. We're looking at this B moving to here. So B's are for 1 and for 2. For 2 isn't nil, for 1 isn't nil. Are both nil. So we're gonna have no destination. I know we should hit this one. Oh, I'm looking for nil position. Okay. So that explains that we were overwriting values. We could never how I ended up. Valid approach doing that. So now we're here. Yeah. Take a look at our next states. We still don't have C moving out, which we need to go investigate. So we have B moving out is moving within its range. C moving out, moving within its range. D moving out, moving within its range. Not this C moving out within its range. I know why that is. Oh, C is already positioned correctly. So fix this bug. Now it looks more like it's actually searching for something, but we're seeing a lot of high values. Everything is in the 1200s here. Like running right into the limit where I start throwing away values because I know they can't possibly be right. I mean, it's clearly traversing. It's given up on. Yes, it's doing a bunch again where it's managed to completely get C in the right spot. Still hasn't found a single correct solution. Interesting that it's just curious as to what happens if we take this approach. I'm seeing a lot more closer to right answers in there. Just like never seeing any where that D ever gets moved out though. Do we want to order them by their rightness? Correctness? Surely there's not that many possibilities in this space. This looks like it's just repeating. Something's wacky in here. It looks very stuck, trying the same things over and over again. And it's like, should be so close to a solution here. It needs to put both B's into here, move the D's over, move the B's in. We're done. I'm just gonna get at day 23 progress. Also, I have a bunch of other. That's the one we're working on. And that's some other specs we don't care. All right. So where do we want to dig into this? Oh, I want to move cost out of the state and start optimizing this. So state. Just back down our costs here. So we're going to keep computing additional cost for a sec here, even if we're not using it in these spots. it in the top. Cheapest cost is going to be cost. That can stay the same. Remove that for now. Keep track of these costs without having them actually tied to these structs. State of correctness. I mean, I guess that's fine. The next state's gonna have to be key hash of states and costs. Or no, what am I doing here? Cheapest cost. Oh, this is why I committed before I started doing this part. that right? And then wrong element type. At 8. Type error. Yeah, we got types in Ruby. Oh. That's exciting. Okay. Why are we just... Okay, well that's not what we want. This correctness isn't a good heuristic anymore. Beautiful code. And this is if 4 is B, then 6, 8. Oh, did I move my print again? would not say that it's doing the right thing. I'm pretty confident that something has gone wrong here. In fact, I want to look at this back. So it's doing this. Let me just back. Next, so this state is this one. I want to see, look at this one. Next states. Print, like we did before. Map first, print. Go. There, it's a hash now. This is not a next state. This is not a possible next state. So it's, let's see. Considers moving B out into its possible positions. Then it should consider moving C out into its possible positions. Then it considers moving the other B out into its possible positions. And then finally it considers moving A out into the A's possible positions. And then for some reason, it's willing to move D back into where it cannot yet go. That violates the rules of this game. It means there is a bug in this code. We need an additional check in here. So if destination to last equals 1, so destination last equals 1 and not correct. Test stuff first 2. And we don't want to go in. Now when D moves out, D does not move back in. Okay. So we've got a bug somewhere. But where was it? It's on line 49. Oh, yeah, that isn't. Hey, look at that bad boy. It's finding solutions now. Now, this is still whack. But we've got our cheater clause in here. Cool. Find the solution. Cool. All right. So the next thing I want to do is optimize things out. Day 23 could work, but too slow. So we know if we encounter now we can throw away some states. We do not need to explore states where we've already seen them with lower values. Can keep track of any state we encounter. We need some way to cache that. I think I need to pass that in to cheapest highest cost, which is kind of awkward, but it'll have to be passed all the way down. So when we hit this cost, we know if scene self scene equals cost. That's the cost of getting. If we haven't seen the state before, we record. So if self, then we have self is greater than or equal to. Sorry, we've gotten here by an equivalent or cheaper means, and we can simply return. Else if, so maybe we should do this. So scene self is nil. Then we do this. Otherwise, if scene self is less than or equal to cost, then we can simply return. Otherwise, we know it's greater. In which case, oh, so if it's nil or if scene self is greater than cost, then we do that. So this is actually just a return if scene self and scene self is less than or equal to cost. Otherwise, I think that's a reasonable optimization. Oh, and we need to continue passing scene down to every call the cheapest cost, unfortunately. Huh. That worked. That's pretty fast too. It wasn't fast, but Your answer is too high. Well, that tells us one thing. Our answer will be lower than that. But shouldn't we have been throwing away values that were that high already? I'm a little worried. This whole doesn't have that turn cost is greater than that. Oh, maybe because we should do that early return as early as possible. We obviously have an actual logic bug somewhere though, so yeah. It's unlikely the answer was just 4 too high. Oh, it was. Amazing. That's really dumb. But it worked. Ship it. Specs fast. We may have to just figure out our issues here, though. As you prepare to give the amphipods your solution, you notice that the diagram they handed you is actually folded up. As you unfold it, you discover an extra part of the diagram. Between the first and second lines of text that contain amphipod starting positions, insert the following lines. So the above example now becomes this. The amphipods still want to be organized into rooms similar as before. In this update, the least energy required is that amount. Okay. That. Day 23, 2. I am going to do something unusual for me and just copy this over instead of inheriting and just modify this one. So it's going to be ugly, but we're going to need to do here and replace the 3s with 4s. So this obviously requires a whole bunch more generalization. We can modify our, this is gonna get so ugly. Just jump around this code and try and catch all of the things. We know we're going to need to change. So that is our new final. This is where we need to make a change. Those were 4s. Then we're going to have some hard-coded values in here. And let's just examine what those were. DCBA, B, C, B, insert mode. Or into replace mode. DCBA, DBAC, DBA. This correctness logic now needs to be even further nested. This should be 4 is A, add 1, then check if 3 is A, and add 1, then check 2 is A, and add 1, then check if 1 is A. Okay. Give this code. A's get replaced with B's. And 2's get replaced with 4's. Capital B's get replaced with C's. Get replaced with 6's. Eights. So that's our correctness. Final looks good. Okay. So position is equal to 4, which is what the equivalent of this case was. Passable's the same. I don't know. Let's just run some specs, see where we explode. I wanted to actually see the states first. I believe that's the correct starting state. DCBA, DBAC, ADCA. Yes. Okay, so that's, we're getting all kinds of jumping through things. States, that's fine. We can generalize this. So if y is greater than 1, then it's possible we could be stuck in our room. If our position y, the spot above us, up to 1, or sorry, down to 1, any right? That means it's an ugly way of writing that, but if we look at the positions above us in the stack, if any of them are there, that means we're stuck here, right? I want to see less teleporting. Okay. Ooh, that was an interesting result. I don't know what I did. Just okay. Let's start. This logic needs to be fixed, though. That's a valid state. It's looking like some weird results. Okay. We know this isn't right. So this should be if it does not equal 0, we need to make sure that all of the ones below it are already correct. Next, square brackets, unless test dot last +1 up to for all oh, test dot last does not equal 4. We're putting it on top of any, those ones need to be correct. That's what I think that's supposed to say. Doesn't look like it's being very successful. We need to just start looking at object states. is looking iffy. Let's see if we can just eyeball, see any other potential issues that we might have introduced. So correct is looking good. States station passable should work the same. Correct. All right, so we're in this. We can do what we've done before. Examine the possible next states. Where we should have B across the top, C across the top, a different B across the top, and a D across the top. So now we have entered into this. Looks like the most expensive first move. And let's see what is produced. Moving B out across the top, moving C out across the top, moving the other B out across the top, and moving A out across the top. Okay, that looks right. So it's decided to move C out. So it's I think what I want is rolling my bind.pry to see if this is actually ever producing correct results. It's not. It's never producing any results. Let's just run that again. We'll do another pass looking for maybe potential logic issues. But yeah, it doesn't look like it's ever finding anything. Okay, well, that's good. I mean, it shouldn't, given it errored, it shouldn't have found anything. If y is greater than or equal to 1, we are in a room. If y is greater than 1, then we could potentially be blocked in this room. So we confirm that we aren't. So we check our correctness. Maybe let's put that in the printout. Correctness of 4 because it has 1, 2, 3, 4 correct. 5, 1, 2, 3, 4, 5. See how close it's getting here. Print if darkness is greater than 8, let's say. Greater or greater than or equal to 8. Getting so close, computer. Let's just look at only the rightest of the right answers. How close does it get? Does it get to 10? Sorted by their correctness and then their I could reverse it, but I don't think it's going to make any meaningful difference. Find some of these decent answers earlier. And it never finds any good ones where the D ends up on the What are we missing? Oh, it might be. Ha! Of course, that's not. That's ruining us for sure. Okay, so we're working. We don't really know how. I'm just gonna set this to 5,500. Sure, 55,000. Try and solve part 2 here. So we did have it right. We just left that constant in our code that we were using to throw away, obviously, too high answers. It's possible this could be too low. Our answer could be over 4,500, but it's not. All right. That was fun. Thanks for coming. That was a fun one. It was tricky. Use some brain power. I'm going to try tomorrow to do day 24, maybe day 25 too, depending on how it goes. But yeah, see you in the next one.